Welcome to Lecture 2, Part 2, on the Engineering Problem Solving series on Education is Power Educational Videos channel. The only place where you can get smarter by listening to dumb people. Got a new mic today, guys, so hopefully the audio quality is going to be significantly better. Let's jump right into it today. We're going to be talking about derived dimensions, equation laws, and conversions using the equation laws. So first things first, let's do a little refresher on our fundamental dimensions. So our fundamental dimensions, let's just put it up here. Now, if you guys remember from Lecture 1, we have a few that we're going to use. I told you that there's two that we're not going to use, so I'm not even going to bother putting those into any examples today. We're going to stick mainly with our M, our L, our T, our theta, and our N. Now, let's remind ourselves what this is. This is mass, length, time, temp, and amount of substance. And these are generally in grams, some sort of meters, seconds or minutes, usually going to be degrees Celsius if we're talking about metric system. And then here we're talking about mole. And again, don't worry about the mole so much. Seems a little overwhelming that we talk about it early on without explaining it, but we will get to explaining it later. Now, the point of fundamental dimensions is you have to understand that during the time that we work through these courses, or through this course and through these problems, you're going to see certain series of units. You might look at a unit and it may be very, very confusing to you, but if you look at it in the fundamental dimensions, you'll realize that this unit can actually be all of these. It might be 5 or 6 different things, can all be put into just one unit. Now, the thing that we need to understand first is derived dimensions. Okay? Derived. Man, my handwriting is terrible today. Derived dimensions. There we go. Kind of getting it. Let's go ahead and underline these. All right. So derived dimensions. There's certain things, and you have to, we're going to go back and I hope you watched the video before this and you familiarized yourself with how exponents work, because we're going to look at that. And I'm going to show you that we use a system sort of like this sometimes when we're doing a fundamental dimensions analysis of a specific thing in an equation. We map it out with one of these. So derived dimensions are when you have dimensions that, how do I explain this? That are present that also could be something else. Just like I said earlier, they can be combined into something else. So like a prime example, let's say we have an equation, right, that says, we're not even going to put anything over here on the left side of it. We're just going to write an equation real quick. We're going to say that we have meters times feet. Let me bring that back real quick. That was sloppy. Times feet times miles. Now, this is astronomical, obviously. Anytime you throw miles in, that's a very large distance. But if we look at this fundamentally, right, and we just figure out that what we're doing here is we're actually dealing with the fundamental dimensions, we can look at this and say, okay, we're dealing with a length times another length times another length. Now, that being said, we know that the solution to this is going to be some length cubed. Now, when we talk about a length cubed, one of the more familiar geometric equations that you should be familiar with is the equation for area. When we're looking at the area of some sort of square, right, we decided that that is length, well, actually, yeah, we'll do that like that. Length by width by height. L times W times H. Fundamentally, this is the same as a length times a length times a length. And this gives us the volume of this square. And the same thing applies over here. Here we're dealing with the volume again. We're dealing with 3 lengths multiplied, and that is volume. So L raised to the power of 3 is equal to volume. And that's a pretty simple concept. So even though we have miles here, this actual solution could be just about anything. It could be gallons. It could be cubic millimeters, cubic feet. However you want to look at it, any volume we can convert this value into it and get a large volume. So let's look at some other derived dimensions. Let's look at some other ones. What about if I told you I had an area that was meters by miles? What is that going to be? Well, it's going to be a length times a length, bringing us to a length squared. Now this one should look familiar as well, because we know that if we have a area, a square, or anything that we have a formula for, we know that the area of this square is length times width. Length times width, which is a length times a length. So that gives us length squared, and this is an area. So therefore the answer to this could be in acres, it could be in foot squared, it could be in meters squared, it could be in anything. And this is going to be L squared equals area. These are pretty simple, right? So let's look at another one. Let's look at, what if I told you to go 100 miles per hour? What are we dealing with here? What is this? This is another, if we look at this one again, and we try to look at it fundamentally, what we're looking at is we can ignore the value. Values don't matter when we're looking at fundamentals. We just want to see fundamentally what this is. This is a length per time, right? And what this is this is the velocity at which we're traveling, velocity. So it doesn't matter if we're doing kilometers per minute. Doesn't matter. All of it is the same. It's all a velocity. And then there's also another one that derives from these things, and this is acceleration. Acceleration. And that's going to be equal to a length per time squared. Okay, so one of the most important accelerations we're going to talk about, and we're probably going to do, I think I'm going to use it as an example here in a little while, for looking at how these things fundamentally click together. But one of the most important ones for this class is going to be this one right here. It's 9.8 meters per second squared. And what this is this is the acceleration due to gravity on Earth. This is the acceleration due to gravity on Earth. So just to break that down, basically, this is the, if we were to look at a graph, okay? Let me scroll down a little bit. Let me just line this out for you guys. If we were to look at a graph, okay, and here's our graph. And I told you to travel from your home to the store. And I'm going to graph basically your distance per time on going to that store. Well, when you leave, it's going to have a little increase here because you're going to speed up. And then you're going to hit a pretty smooth, and then, oh, we're going to hit a red light. So we're going to stop, and we're going to be there for a minute, and then we're going to go back. And now we're on the highway, so we can go a little bit faster, right? And then bam, that's half your trip clocked. These areas here, matter of fact, let me do this in a different color. These areas here, these are velocity. Because here there's clearly a steady distance that you're going for this period of time, right? So for that whole section here, you are going this distance per this time, okay? And that creates a velocity. But these areas here, from here to here, from here to here, and from here to here. Also, let me highlight this one in blue too. This area here, would also be a velocity. Even though you're not going anywhere, that's still zero velocity. These areas, though, these red areas, these are called acceleration. And we're not going to get too much into this concept, but later on in calculus, you're going to learn about derivatives, and you're going to find that what you're looking at in a derivative is the rate of change. So if I'm looking at an x value here, x1, and my second x value is here, and this is x2, and the x value grows as it gets to x2, and I take the derivative of this, what I'm going to have is the rate of change from x1 to x2. And acceleration is just that. Acceleration is the rate of change between 2 points when dealing with the velocity. It's the rate of change of velocity. And you can't ever have just a straight velocity. Nothing ever goes just a straight. There has to be some ramp up to the speed and some ramp down from the speed once that object stops. So we'll talk about acceleration due to gravity a little bit more in detail, but just to give you a general idea of what acceleration due to gravity is it's the rate of change. If I was to drop something from a very high place, off the top of a building perhaps, right? Our rate of change at which this object falls as it speeds up towards the ground, that is 9.8 meters per second squared. That's a very important concept to understand, and we'll actually, I think what we'll do is when we go to fundamentally evaluate this in a minute, we'll discuss how this value was discovered by Newton and how he came to this conclusion, and hopefully that'll make it make a little more sense for you. So we understand derived dimensions. Now let's look at some other derived dimensions that we're going to become familiar with throughout the course of this actual course. So there's something called force. Actually, we're gonna leave voltage out, because we're not really touching on voltage. So we're not going to talk about voltage. Let me put the pin down. I'm going to make us another little chart here. And we're going to do 1, 2, 3, 4. Okay. Oh, and then we need to divide it top ways. Let's do that too. Let's do it Newton. Let's go there. And then this will just be a short one because I'm only going to put the symbol here. We'll put base SI units here. We'll put an explanation of what it is, I guess. And then out to the side, we will put the fundamental dimension. Fundamental dimension analysis of each of these. All right, so let's start off, get the pin turned back on. Let's start off with force. And we're going to do a lecture pretty much on each of these. I might combine them depending on, I don't want the lectures to be super long, but it's looking like they're going to be. Force, the base unit for force is Newton. And that's just a capital N. And 1 Newton, oops, there we go, is equal to 1 kilogram meter per second squared. And what is a Newton? And what is force? Force, as described by Mr. Newton himself, is equal to a mass times an acceleration. Okay? So fundamentally, what is this? Kilogram meter over second squared. Well, kilogram is a mass. Meter is a length. Second squared is a time squared. So like I said, we're going to have things that we can actually replace an entire series of multiple units with just one thing. And this is a perfect example. If you have something in the form of a mass times a length over a time squared, that you can make that a Newton just by converting it to kilogram meter over second squared. Now you can't take a gram foot over minute squared. That's not equivalent to a Newton. But if you convert that into a kilogram meter over second squared, then you can claim it as a Newton. Now there's energy. And that's going to be joules. And one joule is equal to 1 kilogram meter squared over second squared. And energy is equal to force times distance or length. So it's basically, if you're looking at it this way also, you could say that 1 joule is equal to 1 Newton meter. And that's going to actually be equivalent to this over here. If you were to multiply, let's just do it over here actually. If we were to multiply a kilogram meter over second squared times a meter, we can imagine that this meter is basically the m over 1, and we just multiply across, and we get kilogram meter squared over second squared. So what is this fundamentally? This is, again, a mass length squared over time squared. And we're going to take a moment to actually convert some of these into the chart that I had above, because it's interesting, and it also brings into play the negative exponent rule that we learned in the previous lecture. So what's the next one? The next one is power. Power. And powers are watts. Okay? And 1 watt is equal to a kilogram meter squared over second cubed. And what is power? Power is equal to energy, I'm just going to use an E this time, over time. So another way we can look at that is 1 watt is equal to 1 joule per second. And that's, again, that's equivalent. These things all feed into each other, right? So let's fundamentally analyze this one. And we have a mass, a length squared, over time cubed. And the last one we're going to look at is pressure. Pressure is a Pascal. And there's other, it's not just newtons or joules. There's other units that are used for these. These are just the base ones, the normal ones that we see. And 1 Pascal is equal to a kilogram over meter seconds squared. And what is pressure? Pressure is a force per area. P is force per area. And so it's easy to say as well that 1 Pascal is equal to 1 Newton, right, per meter squared. And what is this fundamentally? Well, this is a mass over a length time squared. And so these are the main ones that we're going to be looking at throughout the series. And those are important, and you have to start recognizing them early, okay? Now, let's do this fundamental dimension in a chart, as we did above. Let me actually draw this chart out. We're going to draw... I'm going to switch over to the mouse real quick. Let's draw this chart out. So we're going to have mass, length, time, temperature, and amount of substance. Let's turn the pin on. Mass, length, time, theta, n. And then let me select this. We're just going to copy it. That way we can use it again. All right. So let's start with force. And that's going to be over time squared. So the way we're going to look at this when you chart it out fundamentally is we're just going to put the basic number of the units in here, the exponent of the units. So mass, we only have 1, so we're going to put a 1. Length, we only have 1, so we're going to put a 1. But time, we have time squared in the denominator. Now, you remember, our rules of exponents stated that a negative exponent is a positive in the denominator. So here, we're going to say that the exponent for time is a -2. And that's because this can be displayed as MLT -2. And that's equivalent, because raised to the -2 means that we could put that t to a +2 in the denominator, which would make it the same as over here. Now, let's do another one. This time we're going to, oops, I swear that paste version, every time I try to Control V, it never works. This time, we're going to do, let's just jump straight to pressure. Or actually, let's do power. It's one of the bigger ones. Let's do power. Power, and that is a mass length squared over time cubed. Okay? Now, very simple. We're just going to put 1 for the mass. Length is squared, so we're going to put 2. Oh, and these right here, you just put zeros, by the way. Time is to the -3, 0, 0. And this is how you do a fundamental analysis of something. And this can also be rewritten as ML squared t to the -3. Now that we understand this, let's move on and let's talk about equation laws. And I briefly touched on these in the first half of the lecture. We talked a little bit about them, but we didn't go into super duper detail because that's what we're going to do here. So we know when we're looking at something. Let's give us some. Let's look at an example, because when we're looking at things, we know that we have certain rules that involve fractions, and these rules come into play here, but they have different names to them and things like that. Like the common denominator is actually called the plus law, and we're going to break into it. But let's just look at a quick example to explain kind of why this is important and why we need it. So let's say we're looking at a problem, and we're going to say that in this problem we have a value d, and what that's equal to as far as its dimensions are concerned, this d is going to be let's say it's newtons, okay? And then let's say we're looking at a u, and u is going to be equal to let's say it's going to be millimeters. And we're looking at an m. M is going to be equal to let's say m is going to be equal to millimeters. No, we'll do it feet. And let's say we got a b, right? And our b is going to be equal to let's say it's going to be equal to kilograms per cubic meters. Now, let's take the fundamental dimension of all of this. Well, now before that, let's say our equation is going to be d equals u plus m plus b. That's how you to fundamentally evaluate this equation. Let's see if this makes sense. Let's see if we can actually make this equation work. Let's fundamentally evaluate it. So we know d is a newton. And from above up there, we can see that force is done in newtons. And that's just going to be basically a mass times a length over a time squared. And we know that u is a millimeter. So that's going to be a length. And we know that m is a foot. That's going to be another length. And b, we have a mass, kilograms, right, per length cubed, a volume. This can't work. We've proven that this can't work because we need, in order to add all of these, we need that common denominator. So we cannot add a length to a meter per a length to a mass per length cubed. It doesn't work that way. You need the common denominator. And so what this is called, we're going to change colors to make this stand out. This is called Plus's law. This is called Plus law. And what it states is that every term being added or subtracted must have the same fundamental dimensions. Now, that being said, it's important to note that on occasion, perhaps on a test or something of that nature, you're going to see problems like this, but instead they will leave out an extra variable. So they'll have something like, trying to think of a good example. Here's a simple one then, because I can't really think of a good one. But they could say we have a D, and it's equal to U plus M. And then they're going to say U is a meter. What is D and M? In this scenario, you're being told to assume that this is a true equation, a well-formed formula, as we like to call it, and that it works, that this actually works. And in that situation, you have to reference plus law and say, well, I know that U is a length. And I know that we're adding, which means that M must also be a length. And a length plus a length would equal just a length. It's that simple. So keep in mind plus law. Now, let's think of another couple problems here, because there's another one that's called the unit law. Let's write it out first. The unit law. The unit law. Every term in an equation must have the same units so that arithmetic operations of addition. Oh my lord, I don't even know how to spell. Let's just bring it back. And subtraction can be performed. Now, there's a second part to this rule. Now, that's something that's obviously, that basically covers plus law. We've already said that. We know that. But there's a second thing to this. A dimensionally consistent and unit consistent equation is not necessarily a valid equation. Look at that. Oh, sloppy handwriting. Valid. Equation in terms of physical meaning. All right. So we know that, based on the plus law, that units have to be consistent. But what we're saying here is that it doesn't necessarily, just because the units are consistent, mean that the equation makes sense. Say I have an equation. Wow, that thing drew a bunch of little dots there. Let's say I have an equation of D is equal to U plus M plus B. And here, I say that D is equal to the mass of the Earth. Oh, Lord. Excuse my grammar typos, guys. Not even typos, misspelling. And let's say that U is equal to the mass of automobile. Not any specific one, just a automobile. Good Lord, I cannot spell today. Mobile. And let's say that M is equal to the mass of Randy's leg, which is very close to the mass of the Earth, I'm assuming, but we're not going to get into that. And B, what could B be? Let's say B is the mass of a chimichanga. Now, I'll say a taco. Of a taco. Now, this is all mass. This is all mass, okay? So, this is not only dimensionally consistent and unit consistent if these were all in the same, let's say these are all kilogram, right? All of these are in the form of kilograms. This is not only dimensionally consistent, now it's unit consistent. Now we got the same units all the way across the board. But this equation is not valid because if you add an automobile to my leg to a taco, and those values are not going to equal the mass of the Earth. It's very simple. That concept should be easy enough, but we want to draw it out to make sure that everybody understood it. So that's all that's saying. Now, let's move down and let's talk about multiplication and division. Again with the typos, Randy. What's going on? Mult and division. We have a new law here, and this one is called the per law. And what it states is that when parameters are multiplied or divided, the dimensions and units are treated with the same operation rules as numerical values. Okay. Now, what this is saying is basically what we kind of went over with the previous lecture, the first intro to this one. What this is saying is that the laws and the rules that we discussed regarding fractions also apply to the units. So remember how I said that if we have a fraction, 5 over 4, and we multiply that times 3 over 5, we just multiply across, and we get 15 over 20. Well, the same thing applies to units. So if we have 5 grams over 4 what can I put down here? Newtons times 3 degrees Celsius over 5, we got a gram, Newton, Celsius, what are we missing? Well, let's just throw in a watts. We just multiply across, and we come to 15 grams degrees Celsius per 20 Newton watts. And then the same thing applies for canceling. So if we're looking at 7 grams per 3 degrees Celsius times 1 Newton per 3 grams, we see that these grams cancel. Because we're going to divide in the long run if we don't cancel them. Let's just look at that if we don't cancel them, because I don't think I really discussed this very heavily in the previous lecture. If we go across, we're going to have 7 Newton grams over 9 degrees Celsius grams. And what's a gram divided by a gram? Well, it's just the number 1. Just as if this was a 5 divided by a 5, it would just be the number 1. So we just remove these grams, and our in solution is 7 newtons per 9 degrees Celsius. And that's all it's saying, basically, is that the same things that we're used to dealing with as far as division and fraction and multiplication, those apply here. So if we take 5 grams times 20 feet, we're going to come to 100 gram feet. That's all it's stating. So let's do some conversions involving equations and things like that. Well, no, we won't do it. Let's fundamentally analyze. Let's fundamentally analyze a fun equation here. Let's talk about PV equals nRT. And what I want you to do is prove fundamentally that PV equals nRT works. Now, we're gonna really discuss PV equals nRT later, but for now, let's give you a little bit of let's give you a little history on the PV equals nRT and what that is. PV equals nRT is a equation that basically allows us to figure out what the amount of pressure is if we were to store some gas in a container, in a closed container. And this was invented in like 1830s by a French physicist named Emile Clapeyron. It's really cool to me, at least. I don't know if it'd be cool to you guys, but it's cool to me because he used a bunch of different laws. Like he used Boyle's laws, Charles' law, Avogadro's law, which we're going to do a whole section on later. He used all these different laws to really come to the conclusion that PV equals nRT. So we're going to prove fundamentally that that this equation would work. So in this situation, what happened to my pen? Oh, there it is. Okay. So in this situation, P is equal to pressure. V is equal to volume. N is equal to the capital N, the amount of substance in our fundamental dimensions, but here we're going to call it a mole because that's the unit for it, right? Our R is what we call the ideal gas constant. And it's a set number that we always use in this equation. And there's 2 different versions of it that have, at least 2 different that I know, that have different units. But for this example, we're going to say that its units are going to be atmosphere liters per mole Kelvin. And T is going to be our absolute temperature, which is going to be in units of Kelvin. So, first, let's start off with nRT. What is nRT? And that's all units that we have. So that's going to be a mole times an atmosphere liter over mole Kelvin times Kelvin. Now let's take this and let's put it into fundamental dimensions. So a mole is going to be an N on our fundamental dimensions times atmosphere. Atmosphere is going to be a pressure on our fundamental dimensions. So pressure, if we recall correctly, let me pull up my reference material to make sure I don't mess this up. Where's my reference material? There we go. All right, pressure. That's going to be a mass over a length squared. I'm sorry, not length squared, a length times time squared. Okay? And this times a liter, which a liter is a volume, and we discussed earlier, a volume is a cubic length. All of that over an N and a K. All right? And then that times, oh, we're fundamental, I'm sorry. We're doing fundamental dimensions, I put a K. N and a theta. Because Kelvin is a temperature, and that is our, I'm just going to put some parentheses around this here to make sure we don't get lost. So we got an N. Matter of fact, let me erase this N. I'm going to rewrite it here to make it clear. Times K. Now, oh my goodness, I did it again. Theta. Now, remember we discussed earlier that what happens in this scenario? We lose because this is basically the equivalent of an N over 1 and a theta over 1. And we're dividing by these two. So these will cancel. Right? So we'll be left with simply mass over length time squared times length cubed, which goes to mass length cubed over length time squared. Now we have a length here and a length there, so these can divide as well. So now we're going to erase this length because it's going to go away, and we're going to erase that, and we're going to write length squared over time squared. Now, let's look at PV. Well, we know that pressure is, again, mass over length time squared, and V is a volume, length cubed. This looks very familiar to what we have right here. So if we work this out, we know we're going to come to a mass length squared over time squared. So essentially what we're saying when we say PV equals nRT, we are saying mass length squared over time squared is equal to mass length squared over time squared. This is dimensionally consistent, and therefore the equation should work. We should come to the same units in both answers. So now let's look at an example, kind of streaming all this together. Let's look at an example. Let's say, and I'm sorry I had to take a, may have jumped over and we lost everything on the screen. I had to open up a new file in order to be able to continue to draw. So here we're going to do an example. I'm going to start that over. Let's say you're going to take a trip, and there's two routes you can go. Route 1 is 50 kilometers long, and you can only drive a speed, an average speed on this trip of 36 miles per hour. Route 2 is let's say it's 65 kilometers long, but you could drive 50 miles per hour. How long does it take to complete each of our routes? And we want the how long in minutes to complete each route. So first, we have to understand something. We have to understand that velocity is equal to a distance per a time. Okay? Velocity can also be referred to as speed or however you want to refer to it. Now, this could be algebraically manipulated. We could say that because we have d over t is equal to v, if we wanted to remove d from this side, we need to multiply both sides of this equation, both sides, times t. And on the right side, you see that the t's cancel, and on the left side, we have it. So we can also say that time times velocity is equal to distance. Now the first thing we need to do is we got to convert our velocities. So let's say we're going to work on route 1 over here. And we'll work on route 2 over in this area. So we have 36 miles per hour. And we're going to set up our train and track. And we know that if you look at your conversion values, 621 miles is equal to 1 kilometer. So we find here, if we do our math on it, find here that we're going to travel at about 58 kilometers per hour. Okay. And basically all we did was we divided 36 by 0.621 and we came to 58. Now over here we have 50 miles per hour, and we're going to do the same operation. We're going to do 621 miles is 1 kilometer. And that's going to bring us to 81 kilometers per hour. And again, all we did was we took the 50 and we divided it by the 0.621, and we came to this conclusion. These miles here, let me change colors. These miles here and here cancel. These miles here and here cancel. And when we multiply across, we're left with kilometers and hours. All right. Now that we have that, we know that distance is equal to time times velocity. But let's take it a step further, because we want to find time, right? We want to find time. So we need time to equal something. So in this situation, if we want to get rid of velocity, we have to divide both sides. Let me take this away. We have to divide both sides by velocity. And in this situation, matter of fact, let me do these cancellation lines up here in red too this is going to cancel out. And what we're going to be left with is time is equal to distance divided by velocity. Okay, so we have our velocity, and we know that we've converted it into kilometers per hour. which was important because our distances up here, if we look at this, we'll just draw a line right there. Here's our distance. And then this section over here, this is our velocity. So we have a distance and a velocity. We're trying to find a time. So all we need to do now is just plug these things into our equation. So here, on this side, we can write it down as time. Oh, give her my dot there. Time is equal to our distance for route 1, which is 50 kilometers, divided by our velocity, which is 58 kilometers per hour. And let's set it up over here as well. Time is equal to, so our distance is 65 kilometers divided by our velocity, our speed, 81 kilometers per hour. Okay. Now, we know that we're dividing by a fraction, right? We got to imagine that this is a fraction. So let's just continue the line through. There we go. So that's the same as what we discussed earlier, which is multiplying by the reciprocal. So we're going to say that it's 50 kilometers times hour over 58 kilometers. And the same over here. We're going to say this is 65 kilometers times hour over 81 kilometers. And we can already see that what's going to happen here, our kilometers are going to cancel. Okay? Kilometers are going to cancel. This is going to leave us with, on this side, it looks to be 0.86 hours. Time is equal to, and on this side, it looks like it's going to be 0.8 hours. Okay. It's much closer than I expected it to be. 0.8 hours. So now, we have to do one more conversion. Now we have to take 0.86 hours, and we know that 1 hour is 60 minutes. And I keep putting this R on there. That's just a habit, guys. I just wanted you to know the H is correct. I apologize. That's a bad habit of mine. And then over here, well, let's go ahead and get the final result here. That's going to be 52 minutes. And then over here, we have 0.8 hour. And we know 1 hour is equal to 60 minutes. And that's going to be equal to 48 minutes. So we find that route 2 is faster by 4 minutes. Now, let's do another example. And this example is more just for fun. It kind of includes some of these things, but not so much. We're not going to do a whole lot of conversions. But what we are going to explain is, where did we get 9.8 meters per second squared for acceleration due to gravity on Earth? Now, let's talk about that. So, later on, I don't want you to focus on this too much, because once we get into our section about force, this will make a little bit more sense. But just for fun, let's take a look at it. A law that we've come up with, that Newton came up with, was that force, like we discussed earlier, is equal to what? A mass times an acceleration. Now, our gravity here, if you remember, let's look at a fundamentally acceleration. Fundamentally is a length over time squared. And that's the same for our gravity value up here. Our gravity value is an acceleration. It's a length over time squared. So force is equal to mass times acceleration. And there's another one that says force is also equal to the gravitational constant. I mean, that's an ugly G. Let's do another one. G, which, I'm going to put it over here. G, and anytime we talk about a constant, it's a number that really doesn't change. And you plug it into equations to find a solution, but it doesn't change so much. So a gravitational constant is going to be 6.67 times 10 to the negative 11, scientific notation, Newton meters squared over kilograms squared. Newton meters squared over kilograms squared. Okay? Now, so it's G times the mass of an object times the mass of another object divided by the distance between the center of those two objects squared. Now let's look at I'm going to draw a little pretty picture here. We're going to have some fun. We're going to look at an example here. We're going to draw, oops, that's the wrong color. Let's try that again. We're going to draw a blue orb. We're going to give it some continents. That's Earth. That is Earth. Now we're going to make a little guy, our little stick figure. Whoop, whoop. And that's our person. So we're going to take our gravitational constant, 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. And we're going to multiply it times the mass of our object, mass 1, which will be Earth. Earth's mass. Mass 2, which will be our little man's mass. And then the distance, the radius, here, let's give it a new color. We call it the radius, but it's the distance between the center of these two objects squared. Okay? Now, one thing we know is that both of these equations give us a force. So what we could say is, and we're gonna actually replace mass, because if we're looking for the force here, mass times acceleration, right? We're saying mass, and we're looking for this individual, M2, we're going to say it's mass times this gravity, right? But we're trying to find this gravity, so we don't have it. So we're going to set the left side is mass times acceleration. But in this situation, we're going to make this mass 2. And we're going to set this equal to a G times M1 times M2 over R2. Okay? Now, and you know what? Matter of fact, we're going to actually, we're going to take it a step further, and we're going to make this A, since we're trying to find gravity, we're going to make it into our G. And G is what we're looking for. Our lowercase g. Now, we know that this is all going to become, for the most part, this. Because that g is going to multiply across, and it's going to fit right in there. So we're just going to erase that. And then we know that we want to find g, so we need to get g alone. So what we have to do, we have to then divide both sides of this equation by m2. m2. Now here we know our m2 is going to cancel. Bloop, bloop. No problem, right? But over here, we now have a weird division. We have fractional division. So we have to imagine that this m2 over 1. And then we have to turn this into, this is going to be g m1 times m2 over r2. And then we divide by the, or we multiply by the reciprocal. So that's going to be 1 over m2. Now, because this is all multiplication, there's no addition happening up here. That means that now we can cancel m2 out as well on this side. So now m2 is canceled from both sides, and we're left with g is equal to g times m1 over r2, r squared. M sub 1 over r squared. So now we can plug in some values. So let's look at some values. First, we know that the radius of the Earth is approximately, so instead of doing equals, anytime we do a is about, we make it a squiggly equals. Okay? Radius of the Earth is about 6,371 kilometers. Easy enough, right? And we also know the mass of the Earth is about, we're going to put it in scientific notation for fun here, times 10 to the 24 kilograms. And we know our gas constant. Up here, we have our gas constant. So let's fill this equation in. G is equal to 6.67 times 10 to the negative 11. And I'm going to leave the units off here. I'm not going to put these units in just yet. Because, well, okay, yeah, we're going to go ahead. We're going to put the units in. Let's just put the units in. So here we have a Newton. Oh, let me go back up here so I can see what I wrote. Newton meter squared per kilogram squared. Newton meter squared per kilogram squared. Turn the pin back on. I had to get up and close the door. My dogs were fighting. Sorry about that. All right. And that's going to be times our, where were we at? Oh, yeah, our mass of the Earth. So that's going to be times 5.97 times 10 to the 24 kilogram. All of this over 6,371 meters. Oh, kilometers, I'm sorry. Is it kilometers or meters? I put it in kilometers. Let's do it 6.371 times 10 to the 6 meters squared. You know what? Matter of fact, I'm trying to teach here, so let's back this up a notch. Let's actually do this conversion and make sure that we're on the right path here. And all of this over, we have kilometers here, but we're using meters. So we need to get this into meters. So we're going to say 6,371 kilometers. We're going to convert this. There is 1 kilometer per 1,000 meters. So we're going to find that break out the calculator on it. 6,371 times 1,000. We're going to get 6,371,000 meters squared. Okay? So now, let's start looking at these units and how they cancel. So first we're going to look at G's units. Okay? And let's just make sure we're going to do a little bit of an analysis here to make sure that all this is going to come out good. And we're going to put this in the proper format. So G is going to be equal to Newton meter squared over kilogram squared. What's actually, you know what? We're gonna move all of this back. Let me get this erased because we're gonna need some room for this. And let's get erase it again. wrong button, and then let's get our pin back. So G is equal to Newton meter squared over kilogram squared. Now, what's a Newton? A Newton is going to be, and we're going to basically put the same thing up, but we're going to put a Newton for what its actual units are. So a Newton is going to be a kilogram meter over second squared. And that's going to be times meter squared over kilogram squared. And this is just the same as this, only instead of having an in here, we've filled in the units. So now we know that we're doing some fractional division here. So first let's combine these top terms. So now we're going to have the kilogram meter times meter squared, which is going to give us a kilogram meter cubed over second squared, all of that over a kilogram squared. Now we're doing the fractional division, so we know, as we've discussed many times, we need to imagine this as a fraction and multiply by the reciprocal. So that's going to give us a kilogram meter cubed over second squared times 1 over kilogram squared. And so we see that here, our kilogram up here is going to cancel out. And our squared is going to cancel out here. Because right here, essentially what we have is a kilogram times a kilogram is equal to a kilogram squared. So if we're dividing a kilogram by a kilogram, we can remove one, and then we just get a kilogram by itself. So now our new unit is going to be cubic meters over kilograms seconds squared. So let's rewrite our equation with this new unit. G is equal to 6.67 times 10 to the negative 11 cubic meters over kilograms times seconds squared times 5.97 times 10 to the 24 kilograms. All of this over. And instead of putting it in again like this, another thing, we didn't really talk about this in the exponents, but I want you to realize that if we have am raised to the n, that is equivalent to a to the n times m to the n. You have to distribute this onto both of these variables. So we're gonna actually square this. These numbers are getting very large, so we're gonna actually square this. Let's do it right here. Whoo, that's a large number. Well, that's a large number. So we're gonna write that number out though. Let's do it. Let's do 40. Oops. I'm gonna have to pull that up on a different monitor, I believe. Let me drag it over. So it's gonna be 40. 589 641 123 123. And that's going to be meters squared, because we distribute the exponent here onto the meters and onto the number itself. So this will be much easier displayed, and this is the benefit of scientific notation. It's much easier displayed that way, but we're not doing that right now. So now let's look at what's going to happen next. We combine these two values. Let me do a red pen. We're going to combine these two values. And in doing so, we know that kilograms, because it's in the denominator here and in the numerator here, is going to cancel. And we're going to be left with a new value in the top, right? So let's go ahead and combine those two values. And we're going to use the calculator again. We're just going to cheat on it. So G is equal to, and let me get, I wish I had my other calculator. I don't know where I set it. I was using it earlier in the lecture. Times times 5.9. All right. And now we're going to get on the top, and I'll put this one in some sort of engineering notation here. We're just going to write it out. Forget it. We're going to write it out because it's already on the calculator that way. I don't feel like retyping it. So now we're going to get 3,398,199,000, 000, and 000. And that's going to be in the form of meters cubed over seconds squared, divided by our really long number here. We're just going to actually select that and copy it and paste it. Oh, that didn't work. Technical difficulties here. Let me use the mouse instead. Pins want to act up. There we go. Let's edit, copy, edit, paste. I really wish Control V would work on here. Right here. So now without retyping in or writing these numbers that are very long, let's look at what's going to happen with our units. Our units are going to become, we have to imagine that this is a fraction, again, in order to multiply by the reciprocal, and we're going to end up with meters cubed over seconds squared times 1 over meters squared. And this meter is going to cancel. These are going to cancel. Because essentially what we have here is m times m times m. And down here we have m times m. So this can cancel, this can cancel, this can cancel, this can cancel. Leaves us just with the meter. And that puts our final units in the form of meters per second squared. Now, that's acceleration, right? And let's actually do the division on these numbers. Let's do it. I'm going to pull the thing over here. I wonder if I can I copy this? Yeah, let's try that. And then let's get that back up. And let's divide that by that. And look what we get. We get 9.81. 9.81 meters per second squared. Which is why we say it is 9.8. Now this number isn't precise. Because if we go back up and we look at our drawing here, we're not really clarifying where he's standing. And that radius distance, that distance from the middle of our person to the middle of our planet, can change. If he's on a mountaintop, it'll be different. But this is a general value for gravity on Earth. And that's how they came to the conclusion of this value. And that's why we use it. That will conclude Lecture 2. Thank you guys for watching. Again, if you have any questions or comments or concerns, please put them in the comments. I hope you guys give this thing a thumbs up, subscribe to the channel, and we'll see you for Lecture 3.